So, in this class we are going to discuss about the other solid state reactions, but let me remind you that for the solid state reactions we have discussed that we are going to take up 3 different types of reaction. First one is the Eutectoid reaction. This is what is this, gamma going to beta plus alpha, beta plus gamma, sorry, alpha going to beta plus gamma, and that is what we discussed for the steels. Basically for the steel most important reaction is this pearlite formation reaction, and that is a Eutectoid reaction. So, I know that that reaction is given by gamma going to alpha plus Fe3C. And the left side I am just showing you the phase diagrams, appearance of the phase diagrams if such a reaction is present. This is again taken from Professor Alan Sprint's book, you can look at it carefully. So, we have a lot of discussion for the last maybe I do not know maybe 8-10 lectures we discussed about that, and that towards brought about steels and the cast iron. Another next important reaction is basically the Peritectoid reaction, which is shown at the last here. You see Peritectoid reaction is exactly opposite of Eutectoid reaction, alpha plus beta going to gamma, sometime confusing. If you look at this beta plus gamma going to alpha, so if you take the other side beta plus gamma going to alpha is what is Peritectoid reaction by the way. And so that is basically predominantly seen in some of the phase diagrams which we will discuss. And the second one which is also seen is the monotectoid reaction. As you see, monotectoid reaction is what, alpha 1 going to alpha 2 plus liquid. If you go back to the monotectoid reaction is what, monotectic, liquid 1 going to liquid 2 plus alpha. This is exactly same as solid state, Al1 and Al2 replaced by alpha and alpha 2. So, alpha and alpha 2 have same crystal structure and their compositions will change, beta will have different crystal structure. The structure in the phase diagram how it will be seen is looking like this, alpha 1, alpha 2, beta, and this is the monotectoid transformation temperature, correct. That is what is we are going to study these reactions in more detailed manner. So, you know first I will take up the Peritectoid reaction and discuss about it, then I will take up the monotectoid reactions. About 10 minutes each of this reaction I am going to spend, because these reactions are not so predominantly observed in the phase diagrams, that is why. So, let us first draw a Peritectoid reaction phase diagrams where Peritectoid reaction is seen. Peritectoid So, this is what is the phase diagram, this is temperature axis, this is the composition axis between two components AB, liquid alpha, alpha plus liquid, and then this is gamma plus liquid, this is gamma, alpha plus gamma, beta, alpha plus beta, beta plus gamma. That is what is a Peritectoid reaction thing, but here actually I am showing you both the Peritectoid reaction as well as the Peritectoid reaction. So, let me first tell you the Peritectoid reaction. This is the Peritectoid isotherm. This is the Peritectoid isotherms, and in this case for the Peritectoid reaction is alpha plus gamma, let me just close this, alpha plus gamma going to beta. That is what is the Peritectoid reaction. It is opposite of Eutectoid reaction, and this happens at solid state lower temperatures. You know, because you need to have Peritectoid reaction, you need two solid phases. So, So, therefore, any Peritectoid reaction is preceded by either a Peritectoid reaction or a Eutectic reaction or a Eutectoid reaction, all these things are possible. The meaning is that because the reaction requires two solid phases for the reaction to happen. So, you can get only two solid phases when you have a Peritectic reaction like this or a Eutectic reaction or a Eutectoid reaction. So, here actually a Peritectic reaction happens at peritectic temperature, and what is the Peritectic reaction? Peritectic reaction is what? It is very simple, alpha plus liquid going to gamma. We know that one solid phase reacts with a liquid given to gamma. So, that is what the gamma phase field is present, and because of these two phases presence, you have reaction and having a Peritectic reaction. So, we are not going to spend time on the Peritectic reaction as we have discussed a lot. So, what will happen in the Peritectoid reaction? Let us discuss about that. So, let me just take out these things, because otherwise you are going to be getting influenced by that. So, you know that if you have alpha and if you have a beta, alpha and gamma are present like this. So, Peritectoid reaction will happen at the interface like this. Peritectoid reaction will happen like that at the interface, and as soon as the Peritectoid reaction product with beta will form, the interface will be it will form at the interface, and therefore, the contact between these two solid phases will be vanished. There will be no further contact possible. So, any further reaction is possible only when the diffusion of the atoms from alpha to gamma, vice versa from gamma to alpha is possible. Now, if you look at this diagram, at the Peritectoid transformation temperature, Xp alpha of this composition and reacts with beta of Xp beta composition, these two composition, and forms, sorry, not beta, gamma, this is gamma end, right, and forms a beta of this composition. So, that means beta composition lies between alpha and gamma, correct. So, if you want to form more beta, and where only by diffusion of atoms from alpha to gamma or gamma to alpha, as I said. So, which atom will diffuse from alpha? A, because alpha is rich in A, because this is the amount of B. So, A will be the rest amount, quite a lot. So, A will diffuse this way, and again gamma is rich in B. So, B will diffuse this way, and when they will come in contact, atoms will come in contact, and it has a definite compositions of Xp beta, then this solid layer will form. That is how it happens. So, therefore, initially they will come in contact and form a thick layer of beta. Any further reaction requires diffusion of A through this layer or B through this layer and come in contact with each other and forming more amount of beta. And you know, this reaction normally happens at low temperature. So, because it happens at low temperature, this is highly unlikely that the beta will be formed completely by consuming all alpha and gamma. This is highly unlikely. In fact, it does not happen. What actually happens is that you have all the three phases remained in the microstructure, all the three phases remain. You cannot actually have a complete reaction possible. Even if you keep the sample at this temperature, diffusion is not sufficiently enough. So, this is what actually the problem of all Peritectoid reactions present in the phase diagrams. So, now as I told you that the Peritectoid reactions are not widely seen. So, I am just going to tell you some of these phase diagrams. The first one is the silver aluminium phase diagram. This is option from the FactStage free website. See, there are two Peritectoid reactions here. First, let me discuss about this one. Okay, you see here, this is the phase, single phase. It forms by, this is alpha, this is gamma. So, alpha plus gamma going to beta, correct. You see this is what happens. Not only that, here there is a peritectoid reaction which you cannot see here in fact, that is because there is a phase here alpha plus something else, I think it is either delta also can lead to formation of gamma. This is the way reaction happens. So, there are two reactions here, one is the alpha plus beta, sorry I think I am doing some mistake, let me clarify. This is not this is delta. So, alpha plus and this is beta by the way. So, because I could not get a phase diagram where all these things are written carefully. So, as you see alpha plus beta going to delta, this one reaction, and another one is, no I am making a lot of mistakes, okay. So, this is not delta, this is epsilon and this is delta actually. So, this is alpha plus delta and this is what is beta, sorry, this is what is beta and this is alpha plus beta, correct. So, you can have this reaction, that is what I mentioned here at this temperature. This is the first reaction alpha plus beta going to delta. The second reaction is alpha plus delta going to mu, correct. So, and you know this first reaction alpha is FCC, beta is BCC and this is ACP, delta is ACP. This is more important reaction and more interesting than this one. So, there are two reactions which you can see, this one the second one you can easily see the way I have drawn in the board, exactly same. The first one is not easily observed, but you have to carefully zoom this diagram to see that. So, this is the first diagram which shows you two peritectoid reactions, very rarely seen in the phase diagrams. Now there are a few things I would like to tell you here, and although people not, this is not industrially important alloy, silver, aluminium, and silver is very expensive also, but in this sometime people theoretically study this, and this peritectoid reaction can be modified. As you have seen that peritectoid reaction is very slow. So, therefore, this first peritectoid reaction I am talking about it, this one where alpha plus beta going to delta, and it is very statistically reaction. One FCC phase reacts to the BCC phase, form a ACP phase, very classic reaction. So, if you want to study theoretically phase transformation, this is a very good system in solid state system. Now, if it had been observed that you can bypass this reaction as just like a peritectoid reaction can also be bypassed. So, alpha plus beta and react and form delta massively, okay. This is called massive delta M, Ma, you can form that by massive transformation, okay. Or rather alpha can directly transform to delta by massive transformation, that is also possible. And when this forms this delta, then delta will have a similar crystal structure as the equilibrium delta which is present. This is not equilibrium delta, this is massively transformed delta. Massive transformation delta means the compositions of delta will be same as the composition of alpha from where it is forming. So, let us not write like this, this is what can happen, alpha can massively transform to delta and then this can transform to later delta. So, this is one way of making faster way of delta formation. Okay, so that is about the first peritectoid reaction, first thing about peritectoid reaction. So, now I am going to move into the second one, that is the monotectoid reactions. As you know, monotectoid reaction is basically liquid state solid state variation of the monotectic reaction, and let us do that here first in the board. one reaction which is exemplary is this alpha 1 going to alpha 2 plus beta. So, phase diagram where this can be observed look like this. Normally this is basically a schematic phase diagrams. So, this is a liquid plus alpha. So, you have alpha and this alpha will transform to solid state transformation. Again you will have a loop. These are the different phase boundaries. So, as you see here, this is the critical temperature, same as like monotectic reactions, critical temperature for monotectic reaction, this is the monotectoid temperature. So, at the monotectic temperature, alpha 1 transform to beta plus alpha 2, that is what I showed you, correct, in the phase diagram. So, basically you need a prerequisite alpha. That is why this alpha normally forms by such a kind of phase diagrams, but it can also form by other reactions like peritectoid reactions possible, and then it can undergo such a kind of transformations. This is widely observed. So, basically these two things will have same crystal structure, alpha 1 alpha 2, same crystal structure, but beta will have different crystal structure. The composition will vary. See, alpha 1 has a compositions given by this point, alpha 2 has a composition given by this point at this monotectoid temperatures. So, that is the difference. So, this is there in the book. Now, two systems I am going to discuss where these things are observed. One is known as nickel zirconium. As you know, zirconium happens to coexist into two crystal structures. Room temperature it is ACP, high temperature it is a BCC. So, one can actually transform this high temperature phase which is BCC beta monotectoidically to alpha plus niobium dissolution, that is what is shown here. So, you see here this is exactly same as what I have drawn. So, at high temperature you have isomorphous phase diagrams leading to formation of beta niobium zirconium solution which is BCC, and then this transform into alpha zirconium and plus this is basically beta 1 plus beta 2. So, this is beta 1 and this is beta 2, and here the critical temperature is 988, monotectoid transformation temperature 620. So, therefore, these two beta will have BCC structure, alpha zirconium has a ACP structure as you see here. So, this reaction is like this, beta 1 going to beta 2 plus alpha. So, beta 1 has a BCC structure, beta 2 has a BCC structure, alpha has a ACP structure. This is only because of this structural differences of the zirconium low temperature and high temperature phases, that is why it is observed. But one can also have different thing possible when you have aluminium zinc system. In aluminium zinc system also you will have a this is a classical eutectic system. So, you have a large solid solubility, then eutectic reactions, and this leads to liquid plus alpha, and this one transform into alpha 1 plus alpha 2, and then this is where this FCC A1 alpha plus this is suppose gamma or beta. So, this will be alpha 1 plus this is alpha 1 plus beta. So, reaction is alpha 1 going to alpha, I am sorry, this will be alpha 2 plus beta. This is the monotectoid reactions. That is how things actually happens in monotectoid reaction, but here there is no such thing happened like nickel zirconium. Nickel zirconium actually remains in two different kind of states, that is why nickel zirconium has such a kind of structure, but in this case it is not the case. So, therefore, such a kind of thing is not true. As you see here, the compositions of alpha 1 and alpha 2 can vary. This is the alpha 1 composition, this is the alpha 2 composition. I think this is alpha 2, yes, cannot be alpha 1. So, that is what is correct, alpha 2. So, as you one thing you understood, this diagrams, these phase diagrams are very uncommon, that is why we are not used to it, I am not used to it, these phase diagrams. So, sometimes I am also making mistakes, but you have to read it properly to understand that, but you can correct that, that is the way I am doing it, you can correct these phase fields. Okay, so with this actually I complete my short lecture on these solid state reactions. Now, in the next class we are going to take up few ceramic phase diagrams and show you how the ceramic phase diagrams actually can be read or can be interpreted, but obviously we will take simple ones like solid solution, eutectic, peritectic, or maybe some solid state reactions. So, we will spend few lectures on that, and before actually we move into something else like ternary phase diagrams. Thank you.